Fast algorithms result in fast programs, so it is important that we try to minimize the time consumed by our algorithm. For example, consider the following pseudocode that describes a certain algorithm. And by the way, please don't try to actually understand this algorithm, because I'm not even sure if it actually does what it claims to do. This is just a toy algorithm that I wrote to show you all the possible kinds of statements that you might find in a typical algorithm. It has a loop, it has conditional statements, it has a print statement, it has a read statement, it has a return statement, it calls a helper function, so it has all the bells and whistles. And now, let's say that we wanted to find the time taken to run this algorithm. Since we can't actually compile and execute pseudocode, we have to be clever with how we quantify this time. One such way to quantify the time taken to run an algorithm is to measure the number of operations demanded by the algorithm. You can think of an operation as one unit of computation that takes some constant amount of time to perform. Okay, so let's take a closer look at the pseudocode now. Generally speaking, a single line of code results in just one operation worth of computation. This is because most lines of code involve a manageable, constant chunk of computation. For example, when you try to print something, it takes, well, if the string is particularly long, it may take you some time, but the time taken to print a string doesn't grow with n. So that means that even if the string were particularly large, the time taken to print it wouldn't be a function of n. So in that sense, it is always constant, and most lines of code are like this. They only take a constant amount of computation to perform. Now, the only exception to this rule is when you have a line of code that goes something like this, where you have a loop concealed as a single line of code. Because when you execute this line of code, you're actually executing n lines of code. So the amount of computation that you perform is a function of n. Now, given what I just said, you might be a little bit surprised that I wrote this loop also as just one operation. That is because this particular statement in and of itself only takes one operation to execute. It is just that this statement is visited about n times. So in total, the total contribution of this statement to the time complexity of the algorithm would be about n operations. If you wanted to be a little pedantic, it would actually be n plus 1, because the first n times that you visit this statement, the loop condition would be true, and the n plus 1th time it would be false, and we would break from the loop. But leaving all that aside, we visit this statement n times. So the total contribution of this statement ends up being about n operations, as expected. And you might also be surprised as to why I'm saying that a whole function call is just one operation. The logic behind this is that this statement, just by itself, is only responsible to make the call. It's not responsible for the actual execution of the function. Those lines are separate, and those lines involve computation and operations for themselves. If you wanted to find the total time complexity of a program, you would have to somehow analyze the algorithm and figure out how many times each statement is executed. So let us quickly go through all the lines of the algorithm and try to see how many times each one is visited. This first line is only visited once at the start of the algorithm, and this line is also only visited once, and this one is visited for as many iterations as the loop runs for. The same for this one. And these two print statements together are visited a total of n times. That is because one and only one of these two print statements is executed per iteration of the loop. So if the first one is visited x times, the second one would be visited n minus x times. N minus x times. This is only visited once. This call is only made once. And this return statement is only called once. Since the helper function is only called once throughout the main function, we can be sure that all of these three statements are executed only once. So now all that is left is for us to tally the total number of operations in all these comments. And that ends up coming out to be 4n plus 8 operations. So it's a linear function of n. In the subsequent videos of this playlist, I will post some examples of how you can calculate the number of operations in many different scenarios of code, like in loops, in recursion. But one thing that I really want you to understand is that time complexity is not merely the number of operations performed. Time complexity is something defined a little bit differently, and we will go through the proper definition of time complexity in a later video about asymptotic analysis.